surrounding a magnet, there is a region in which its influence is experienced. That region is called magnetic field. Magnetic field can be represented by magnetic field lines. That concept was developed by Michael Faraday. Magnetic field lines are the lines along which a unit north pole will tend to move if it is free to move. Magnetic field lines are continuous lines. Outside it is from north pole to south pole. Inside it is from south pole to north pole. It's a continuous line. Then where lines are crowded, strength of the field is more. Here you can see lines are crowded. So strength of the field is more here. Here lines are not crowded. So here gap between the lines more. So not crowded. So here weak compared to this. Then a uniform field can be represented by parallel lines. So here you can see gap here and here it is same. So a uniform field can be represented by parallel lines. Then at each point, direction is given by the tangent drawn to the line. So here this is the tangent. So here this is the direction of the magnetic field. So here if you draw the tangent, this is the direction of the magnetic field here. Now here this is the direction of the line. So here this is the direction of the magnetic field. Lines of force will never intersect. Suppose this line is intersecting this line. Then at this point two tangents can be drawn. That means at one point there will be two directions for the magnetic field. So that's not possible. So lines of force will never intersect. Then let us see what is magnetic flux. Magnetic flux is the total number of lines passing through a given area. Then magnetic flux unit is Weber. Next, magnetic flux density, or it is also known as magnetic induction. It is denoted by the letter B. This is a phi B, this is B. Magnetic flux density is the number of lines passing through a unit area. Then it's measured in Weber per meter square. Weber per meter square is known as Tesla. So here there is a uniform magnetic field represented by this parallel lines, and as shown by this arrow, direction is along this. Then in this there is a surface, then that is represented by this vector. Area can be represented by a vector. This area is represented by a vector pointing that side. Suppose it is, then it is represented by this vector, area vector. So area vector is perpendicular to the area. Now flux passing through this area is B vector dot A vector. Magnetic flux B vector dot A vector, that is BA cos theta. Now some special cases. Suppose the coil is like this, or this area is like this. Now area vector and B vector both are in the same direction, so theta will be 0. Then cos 0 is 1, so magnetic flux will be B into A, BA. Suppose the area is like this, then this is the area vector, then this is the magnetic induction. So it is perpendicular. Magnetic induction is along this direction, that is the direction of the magnetic induction. then this is the area, this is the area vector. So area vector, so it is perpendicular, so it is angle is 90 degree, theta is 90 degree, cos 90 is 0. So if it is like this, no flux is passing through this area. If it is like this, full flux is passing. So B into A, if it is like this, flux is 0. Suppose the magnetic field is not uniform, then instead of B vector dot A, B vector dot dA vector, first you have to find out for the flux passing through a small area dA vector, then we have to integrate it. So total flux is integral of B vector dot dA vector.